Hello, my name is Chris Gallagher, and this is my Advanced Functions CCT. The purpose of this video is to explain how to solve my assigned problem using the concepts I have learned in class. The question I will be answering in this video is on page 512 on the Chapter 8 test, and it reads, Carbon-14 is used by scientists to estimate how long ago a plant or animal lived. The half-life of carbon-14 is 5,730 years. A particular plant contained 100 grams of carbon-14 at the time that it died. Question A. How much carbon-14 would remain after 5,730 years? Question B. Write out an equation to represent the amount of carbon-14 that remains after T years. Question C. After how many years would 80 grams of carbon-14 remain? And finally, question D, estimate the instantaneous rate of change at 100 years. Right away, looking at this question, I can clearly see that it is a half-life problem which comes from the 6th unit of this advanced functions course called logarithmic functions. This particular question came from the 4th lesson of the unit, solving exponential equations. The problem is asking me to do 4 things that will be solved in various steps. Question A. How much carbon-14 would remain after 5,730 years? So to solve this question, I will use the half-life equation that we learned in class. So the half-life equation is m of t equals a 1/2 t over h. So A equals the initial value of the half-life. So A in this case would be 100 grams, as the particular plant contained 100 grams of carbon-14 at the time that it died. So A equals 100. T equals time. So in this case, T would be 5,730 years. And H equals the half-life. So in this case, H would equal 5,730 also. So I will now plug these values into the equation to help get my answer. So it will be m of t equals 100 1/2 5,730 over 5,730. So the first step I will take to simplify this will be writing 5,730 over 5,730 as the exponent 1. The next line will be 100 times 1/2 is 50. 50 to the exponent 1 is just 50 times 1. So the answer will be 50 grams. So therefore, after 5,730 years, 50 grams of carbon-14 would remain. When I plug the equation into Desmos, I get a straight line at y equals 50, proving my answer of m of t to be 50 to be correct. So question B states, write an equation to represent the amount of carbon-14 that remains after T years. So for this question, we're still using our half-life problem of m of t equals a 1/2 t over h. So a still equals the initial value. T is our time. So for this one, it's going to be our unknown. And h equals our half-life. So using the same values from question A, we know that m of t equals a 1/2 t over 5,730. So for this problem, we will have to isolate for t to find the amount of carbon-14 that remains after t years. So the final equation will be m of t equals 100 1/2 t over 5,730. So question C reads, after how many years would 80 grams of carbon-14 remain? So we're still using the same half-life equation of m of t equals a 1/2 to the exponent t over h. So a is still going to be 100, t is going to be our unknown, h is going to be 5,730, and m of t, after how many years would 80 grams of carbon-14 remain? So m of t is going to be 80. So plugging that in, we get 80 equals 100 1/2 to the exponent t over 5,730. So the next step will be to bring 100 over to the other side to get 80 over 100 equals 1/2 to the exponent t over 5,730. So 80 over 100 simplified equals 4 over 5, 1/2 to the exponent t over 5,730. So to get rid of that 1/2, we're going to take log base a half to both sides of the equation. So it will be log 1/2 4 over 5 equals log 1/2 So the new equation will be 0.3219280094 equals t over 5,730. So to isolate for t, we bring that 5,730 to the other side of the equation, and since it's being divided, we must multiply on the other side. So we get 0.3219280094 times 5,730 equals t. So t is going to equal 1,844. So therefore, after 1,844 years, 80 grams of carbon-14 will remain. So the final question, question D, is asking, estimate the instantaneous rate of change at 100 years. So instantaneous rate of change is the measure of the slope of a function at one point on a function. So this is from Unit 1, the piecewise functions unit of this course. So the formula for instantaneous rate of change at x equals 100 is m 100 plus 0.001 minus m 100 minus 0.001, 100.001 minus 99.999. So we get these values by adding 100 plus 0.001 and 100 subtracting 0.001. So the next line is going to be m 100.001 minus m 99.999 over 0.002. So to get these values up top, we must sub them back in to our equation for half-life. So the equation is m of t equals 100 1/2 t over h. So we sub in m of t equals 100 1/2 100.001 over our half-life of 5,730. So m of t is going to equal 100 times 1/2 to the power of 100.001 over 5,730. So we get 98.79759433. So doing the same thing, we must plug 99.999 into the same equation. So m of t equals 100 1/2 to the power of t over h. So we get m of t equals 100 to the power of 1 times 1/2 to the power of 99.999 over 5,730. So m of t equals 98.79761823. So now we must sub these back into our instantaneous rate of change equation. So that's going to be IROC x equals 100 equals 98.79759433 minus 98.79761823 all over 0.002. So the next line will be negative 0.0000239 over 0.002. So the final value will be negative 0.01195. So therefore, at 100 years, carbon 14 is decreasing by 0.01195. To end off, a career that uses this type of problem is a pharmacist/doctor because they need to know how much of the drug they are prescribing in the patient's system during different points so they can monitor them and prescribe more if needed. Thank you for listening to this video.